Hello everyone. I'm going to present today about atomic level strain to account for structural heterogeneity and thermal effects. The motivation for this talk comes from a comparison of the failure criteria for mechanical failure at the continuum scale versus at the atomic scale. So, as opposed to the continuum scale, at the atomic scale, failure criteria can be defined independent of the driving factors and also independent of scale. So using this information, we want to see if we can simplify the continuum scale failure criteria. It has been observed recently, for example, in the glass transition of metallic glasses, that the Lindemann criterion can be used to predict the onset of this glass transition. So when the atomic vibration reaches 20% of the interatomic distance, this was found to be a suitable predictor for the onset of the glass transition, irrespective of the driving factors, whether it was temperature or deformation. In our work, we have found that the vibration amplitude normalized with respect to the temperature can predict the onset of elastic instability in single crystal aluminum, and this criterion is independent of the temperature, as opposed to the strain value, uh, which decreases with increasing temperature at failure. Now, in another work, we have also found that a so-called vibration stress, which is which captures the energy due to the change in the vibration, in the atomic vibration, serves as a precursor to elastic instability in single crystal aluminum. Before the actual elastic instability onsets, the vibration stress shows an instability. And coming to amorphous solids such as metallic glasses, there are the shear transformation is the fundamental uh, mechanism which starts off the failure at the atomic scale. And there are several factors which need to be studied. One of them is the dependence on the initial structure, that is, the atomic level stresses and strains, which are uh, already present in the undeformed solid. There have been various predictors for the onset of shear transformations, but they are not a satisfactory one has not yet been found, and it is possible that the vibration stress and vibration tensor could serve as these predictors. So in this work, we are looking at the atomic level stresses and strains in the undeformed configuration, that is the residual atomic level stress and residual atomic level strain. The atomic level stresses have been used to predict the onset of mechanical failure in various types of materials. Uh, the, the atomic level stress and atomic level strain arise primarily from three sources: structural heterogeneity, thermal vibration, and change in the mean positions of atoms. When we are looking at the lattice mismatch, it can be found using X-ray diffraction, and this has been used to calculate the atomic level stresses. However, this only captures one of the three factors, that is the change in mean positions of atoms, but not the structural heterogeneity or thermal vibration. And this is of consequence in various uh, in different instances. For example, while studying the residual stresses and strains, the type 3 residual stresses and strains in additively manufactured metals. So the it is difficult to get a clear relationship between the uh, lattice residual strains, which are measured using X-ray diffraction, and the eigenstrains used in crystal plasticity, and also the atomic level residual stress and the back stress used in crystal plasticity. So, in order to get this a clear connection, the two kinematic measures have been determined. One is the strain, which is purely due to the which is purely capturing the change in mean positions of atoms, and the other, the vibration strain, is purely capturing the change in the atomic vibrations, and corresponding to each of those, the corresponding to the energy change brought about by each of those, the stress can be split into a static and dynamic stress. So here we see the residual strain due to the lattice mismatch, and that is obtained by a comparison of the deformed and the distorted and the undistorted lattices. And here we see a residual strain from the second moments about mean position, that is from the atomic vibration. So we note that in the continuum theory of lattice defects, an incompatibility tensor is what is used to define the residual stress, or is in terms of elasticity, but it is not clear whether the lattice mismatch represents the entire energy associated with the residual stress. So when using a molecular dynamic simulation of FCC aluminum, we are able to show that the atomic level deformation gradient purely from lattice mismatch does not have a one-to-one correspondence with the atomic level stress. Here we can see that at the neighbors where we have tensile atomic level stresses, we have compressive atomic level strains, and their magnitudes are too small to directly produce the stress observed. So how can we obtain the true value of atomic level strain? We can do it in an energetic manner, but can we get a kinematic measure? So we propose to do it using this vibrational strain definitions, and for the vibrational strains, we can see that their magnitudes have a qualitative correspondence with the atomic level stress and with the true residual strains. The main point here is that the lattice distortion, that is the change in equilibrium positions, only corresponds to a very small energy associated with the residual stress, less than 0.1%. So therefore, it is not a sufficient measure of the atomic level residual strain. And the vibrational strain, in fact, captures the spatial distribution of the potential energy. And we can also develop a constitutive relationship between the true uh, atomic level residual strain and the vibrational strain. So therefore, the vibrational strain defined here can serve as a kinematic measure of the residual strain. I want to acknowledge the help given. Thank you.